The third component of our example active treatment system scenario is the reaction tank module. In mine water treatment applications, reaction tanks, also sometimes referred to as reactor tanks or mixed tanks, serve a variety of functions and are designed in an assortment of configurations. In a general sense, mine water treatment can be thought of as an overall two-step process. The first of which involves chemical processes, pH adjustment, oxidation of dissolved species, and flocculation. The second step comprises physical processes that involve settling and collection of suspended particles and clarification of effluent water. Reaction tanks are one of the main components where chemical treatment processes occur. Here is what the reaction tank module looks like when it is first opened. Consistent with other AMDTREAT modules, user inputs are on the left-hand side of the module and calculated outputs are on the right. The module inputs on the left-hand side are arranged into 6 sections: design, flow, input, tank configuration, option information, equipment options and foundation conditions, other capital cost items, annual cost items, and other annual cost items. The workflow for the module begins at the top left-hand side. Enter the design flow, and AMDTREAT then calculates an initial tank sizing summary and related financial information on the right-hand side of the module that is based upon the default value. Next, we can select the Equipment and System Installation heading to select and size treatment equipment. We can use this section to specify the operational frequency and duration of the treatment system to ensure annual costs are correctly modeled. Finally, we can specify additional capital and annual costs not considered by the module under the Other Capital Items and Other Annual Items heading. For our example treatment site, the first step is entering the design flow. Unlike the typical flow, which is used to calculate annual chemical consumption, the design flow is the flow rate selected to size structures and treatment components at the site. Typically, the design flow represents the maximum quantity of water intended to be treated. Hydraulic sizing for the facility or treatment component is based upon this flow value. Design flow rate is used to calculate the tank retention time for the tank size that has been selected in the next module input section entitled Round Baffled Reaction Tank Design. In treatment systems that utilize lime products, either dry lime or lime slurry, reaction tank retention time sizing must consider lime solubility limitations in addition to volumetric and dissolved metal species oxidation mix time considerations. Studies indicate that a minimum of 6 to 12 minutes of retention time is needed to achieve adequate dissolution of lime products. Lime product solubility characteristics are discussed in much greater detail in the AMDTREAT Lime Products Module Tooltips and Help file. Note that for our example treatment site, the default values contained in the round baffled reaction tank design section having a tank volume of 60,000 gallons yields an estimated retention time in the sizing summary section that far exceeds the recommended retention times. Clearly, the default values are not appropriate in this example. In the next module section, entitled Round Baffle Tank Design, options allow for the selection of the type of tank construction material. 3 material options are available: fiberglass, concrete, or steel. Tank volume options are also specified by the program. For fiberglass tanks, we can select from 3 optional volumes: 10,000 gallon, 20,000 gallon, or 30,000 gallon. Concrete or steel options offer a choice of either 30,000, 60,000, or 90,000 gallon tanks. For our example active treatment site, we will select the smallest volume reaction tank, 10,000 gallons. Using the smallest tank selection volume yields a much more appropriate retention time, albeit still significantly longer than the theoretical 6 to 12 minutes to assure adequate lime dissolution and mixing. Future versions of AMDTREAT may have an option for smaller reaction tank design flows, such as our example site. However, reaction tanks often serve various treatment functions beyond just allowing time for chemical mixing and dilution. Some of the primary functions that reaction tanks facilitate in a typical mine drainage treatment system are the introduction and mixing of treatment chemicals, acidity neutralization pH adjustment, conversion of dissolved species to suspended solids, formation of oxides or oxyhydroxides, blending or mixing of mine waters of variable flow or quality if multiple sources are being treated, gas exchange with the atmosphere, either oxygen or carbon dioxide, or both, introduction and mixing of recirculated solids in sludge recirculation or high-density sludge treatment processes, and finally, heterogeneous iron oxidation and sorption of other metals such as manganese and trace metals, where suspended iron particles can, in some cases, promote additional metals removal. The next module section, entitled Equipment, allows for including either a surface aerator or mechanical mixer in the reaction tank. Horsepower and cost can be calculated by the program based upon tank volume, or the user can specify sizing. In addition, operational times, access stairs and catwalks, and a variable frequency drive, VFD, for the aerator mixer electric motor can be specified. For our example treatment site, we will choose a user-specified aerator with a 3 horsepower requirement and a cost of $2,500, and change the default VFD cost to $150 based on the smaller motor size. The next module input section is foundation. The first step in estimating the capital cost of the foundation for the reaction tank module is to specify or accept the default concrete and material placement unit cost used to calculate the cost to purchase, deliver, and form the concrete foundation. AMDTREAT then estimates the foundation based on soil quality selected and the type of tank selected. Fiberglass tanks have a standard foundation thickness of 0.75 feet, and concrete or steel tanks have a standard foundation thickness of 3.5 feet. The foundation volume is multiplied by the concrete and material placement unit cost to estimate the capital cost of the foundation. If no foundation is required, users can make the concrete and material placement value 0 or enter 0 yards for the user-specified foundation volume. The next section, entitled Other Capital Items, allows us to capture the capital cost of equipment and other items that are not included in this module. For example, in some cases, users may want to include the cost of a pH controller, probe, or other monitoring device in the reaction tank. For our example site, we have already included a pH probe and controller under the lime slurry module, so they are accounted for. The installation of those items in the actual treatment system would occur within the reaction tank in order to control chemical addition on the basis of treatment pH within the reaction tank. The section entitled Annual Costs allows for inputting the electrical cost in kilowatt hours. To be consistent with our site pumping module and lime slurry module, we will change the default value from 15 cents per kilowatt hour to 8 cents per kilowatt hour. The final reaction tank module input section is Other Annual Costs. This section allows us to capture the annual cost of equipment and other items that are not included in this module. For example, we could include an annual subscription cost to conduct electronic surveillance on the treatment system. We've now completed all of the input information needed to generate the output summarized on the right side of the reaction tank module. The sizing summary at the top right summarizes the retention time, tank dimensions, foundation dimensions, and motor horsepower requirement. The next section on the right side of the module is capital cost, which displays the equipment cost, foundation cost, and the cost of installation. Installation costs can be specified as a percentage of the other capital costs, or we can specify in a known cost. For our example site, we will opt to specify a known installation cost of $7,500. The annual cost section displays and summarizes annual operation and maintenance costs, which can be calculated as a percentage of the capital cost, or a known value can be entered. Electrical cost as well can be either calculated by the program or entered by the user as a known value. Other annual cost values are included and summarized if input was provided under the Other Annual Cost Input section. The last section is the net present value. There are 8 items included by default to calculate the net present value for reaction tank, including default values for life cycle and replacement percent for each item. The capital cost for each item is automatically used so that any of the cost items is $0, it will not be included in the NPV calculation. Or we can uncheck the box next to each item if we do not wish to include that item in the net present value calculation. For our example, we will leave all of the items included and not change any of the default values. The resulting net present value for the reaction tank component is $87,795. This means an initial investment of $87,795 under an inflation rate of 3.1% and rate of return of 8.45% is predicted to provide the funding needed to sustain the reaction tank component of the treatment system for a 75-year period, including all operation, maintenance, and replacement costs. This concludes the reaction tank section of the tutorial. Next, we will discuss the pawns module in the active treatment tutorial entitled Module 4 Pawns. Thank you, and once again, please refer to the module tooltips and online help files for additional information.